coffee today, Wigan?
Actually, this is tea.
Tea.
It's tea. I stopped drinking coffee. that doesn't make me feel good. Okay. No, it doesn't. I have GERD.
The coffee doesn't or the tea doesn't?
Coffee doesn't.
The coffee doesn't, yeah.
So this is Celestial Seasonings,
Ooh.
Mary Zinger.
Oh.
Okay, so current is charge moving in a wire.
Mm-hmm.
Okay, however, charge can travel without a wire. A stream of protons and electrons can be steered around by magnetic fields. For example, the solar wind is charged particles that stream out away from the sun through space, and it's ionizing radiation. And what happens is these, as they approach the Earth, they encounter the Earth's magnetic field, and that deflects them so that it doesn't come down towards Earth. So the Earth's magnetic field has played a role in evolution by blocking ionizing radiation. But at any rate, if you got a stream of protons and you have a magnetic field, it'll make them move just like the current in the wire. Okay, so for a proton, here we have the X, Y, and Z axis. The velocity is in the Y. Who the deuce made that up? Okay, so here's the right-hand rule for a proton. The magnetic field is up, the velocity is in this way, and the force of motion.
So it's just like current, but the velocity.
Yeah.
Okay.
And for an electron, if you have a magnetic field in this direction, and the direction of the velocity is this way, it'll cause it to curve. Now, do you have the remote for that television somewhere? Oh,
I don't know.
I don't need it.
Wait, so the magnetic field is this one right here, right?
So this is not plugged in.
Oh, I've got a
I'm going to need an extension cord. I know what it is.
So where's the magnetic field? It curved in. My TV's so dusty.
That television was put on that wall in 1994. Yeah, that should be the power button.
Oh, there it is. That noise. Hit that little.
Yeah.
Oh, I love it.
We'll come back to this.
I was so pissed when they took mine out of Science 4
All right.
from Mr.
So,
Jones.
what you have is a magnetic field will deflect.
Wait, can you show me? So sorry, magnetic field is that are the dot?
So here they've got the magnetic field south to north. It's going out of the north. It's in that direction. The direction of the electrons of this, notice I got my left hand here. So the force is going to be down, and that causes it to go like that.
Okay, so you have to say, hey, left hand, electrons.
Left hand for electrons, right hand for protons.
Gotcha.
Huh?
Wow.
So I'm steering electrons around with a magnetic field.
Cool.
Because we'll get to that in a minute. Okay, the force on a moving charge is intensity of the magnetic field, how much charge, like if you've got a doubly ionized or singly ionized or whatever you've got, times the velocity, and then you've got the sine theta. I'm just going to leave the sine theta out for now. But let's just look at this. The current is coulombs per second, and length is meters.
Mm-hmm.
And here, charge is coulombs and meters per second.
Mm-hmm. I see. Yeah.
All right.
Mwahaha, that's nice.
All right, so then just a little reminder here about the charge on a proton or an electron. If it's a proton positive this, electron it's negative. So the force is always perpendicular to the direction of the velocity. The hand rules still work. The direction of the field, the direction of the velocity, and it's the third that it's
the force.
All perpendicular. It's perpendicular. The force is always perpendicular to the direction of the velocity. So what? Well, what would be the shape of the path of an electron beam? Okay? So here we've got the force is constantly perpendicular.
Mm-hmm.
So it causes, regardless of the direction of the velocity, it causes it to move in an arc.
Mm-hmm.
Or if it's completely in, it'll be a circle. Remember circular motion?
Mm-hmm. Wait, how come the force is changing?
The force stays the same. The direction of the force changes.
I see.
The direction of the force changes.
Oh, okay,
It's just like this.
Okay. Yeah.
So the direction of the force
is
always perpendicular to the direction of the velocity.
Okay.
And this is a very useful phenomenon that we use here, we used to use there, and we'll get into other applications of that as well. So the force is constantly perpendicular to the direction of the velocity, which causes curved paths. Okay, it provides, so in other words, that magnetic force, I left the B out over here,
Oh yeah. Mm-hmm.
provides a centripetal force.
Mm-hmm.
So, and as such, it does no work. The centripetal force does no work because
It's perfect.
work is force times displacement in the direction of the force, cosine theta.
Cosine
the
90.
cosine of 90 degrees is 0. So it does no work. It doesn't change the energy of the charge. It just changes the direction of the charge, that the charge is moving.
Makes sense.
So, and once again, this is something we've already encountered. We're just hitting it again.
Thank God. I was be like, what?
All right. So a beam of electrons with this, and this is, we're getting not quite relativistic speed here, relativistic speed. And we will get to modern physics. Travels through a magnetic field of this. If everything is perpendicular, what force acts on the electron? Well,
Force equals the B.
yeah, it's 4 times 10 to the negative 2 Teslas times 1.60 times 10 to the negative 19 coulombs
Negative.
times 3.0. What is the negative or positive going to mean here?
The it just
give
tells
you
if
a
it's
hint.
an electron.
It's the direction of the force.
Oh, sorry. Direction,
No,
yeah.
it's the direction the force is going to go. If you got a proton and the field is this way and the velocity is that way, it's coming towards you. If it's an electron, the field is up, the velocity is in the same direction. It's away.
It's the direction of the force.
So
that makes
that's
sense.
an excellent point.
Because it's a different hand. It's, yeah.
Times 3.0 times 10 to the 6 meters per second. And we get 4 times 10 to the minus 2 times 1.6 times 10 to the negative 19 times 3.0 times 10 to the 6. And I get, holy schnauzer. Is that right? 2 times 10 to the negative 27 newtons. That's not very much force. Okay, I got 4 times 10 to the negative 2, 1.6 times 10 to the negative 19 coulombs. 3 times 10 to the 6. Yeah. So that's 2 times 10 to the negative
27.
27. That is
Just a little guy. Just a little bit of force.
but it's an electron.
Mm-hmm.
So it doesn't take much force to move it around. I should just leave it down on that thing. Come on.
There it is. There it is.
An ion is an you don't need to tell you this anything. So a doubly ionized particle has lost or gained 2 electrons. So the level of ionization, you're going to multiply this times 2 if it's
They'll say it's doubly ionized or something.
Yeah. And so you got to tell that to the kids. I don't have
Yeah.
to tell it to you. So, but all you're going to do is multiply the charge on 1 times what the charge is. All right. A long straight wire shown in figure 1 above is in the plane of the page and carries a current I going that way. Point P is also in the plane of the page and is perpendicular distance d from the wire. Ignore gravity. With reference to the coordinate system, what's the direction of the magnetic field at point P due to the current of the wire? Well, that's simple. Okay, here it's conventional current right-hand rule. So right here it's going to be in, yes?
Mm-hmm. Yep.
Okay, so and it's going to be in, so the magnetic field right there is going to be in. A particle of mass m and a positive charge q is initially moving parallel to the wire with a speed of that when it is at point P, as shown in figure below. So it's got a mass, it's got a charge, it's got a velocity, it's a certain distance from the thing. With reference to the coordinate system, what is the direction of the magnetic force acting on the particle at point P? Okay, well, it's positive charge.
So we use our right hand, and we know the velocity is
Here's the thing. So the velocity is in this direction.
and the magnetic field, the B.
And the field is in that direction. So the field is this way.
So it's,
And the velocity is that way. It's going to be down.
yeah.
Isn't this a beautiful thing? And see what a fair question this is for the test. All right. Determine the magnitude of the magnetic force acting on particle P in terms of the given quantities and fundamental constants.
All right, what do we got here? We got charge, we got
Bqv.
velocity. Yeah. Does it tell us those things?
No, it tells us that there's a magnetic field B.
It tells us it has a Q and velocity. So does it want it does it want it?
Okay, so we don't know B, do we?
No.
All right, so check this out. B is this. So
QVF.
here's the quantity of charge on the particle. Here's how
I
fast
see.
it's going. They don't give us B, because what I did is I went through, I looked at this, there's no B anywhere. They ask you a question, what's the direction of the magnetic field? We got that, but, so did they give us I, did they give us a
They
current
don't give us
wire?
anything. That's what I'm looking at. Like,
No, I'm not talking about numbers. Are they giving you the symbols?
Oh.
Yep, we got I. So, and here's the thing, and this kills kids.
Determine the magnitude of the magnetic force acting on the particle at point P in terms of the given quantities and fundamental constants. Oh, I didn't read the last part. Okay. Boom. So if you put B there, it would be wrong because they don't give that to you.
They would take a point. You know, it's like, do I have I don't have it here, but it would probably be 2 or 3 points.
Yeah. Okay, that makes sense. Sweet. Okay.
Right, and then we got an electric field is applied to causes an electric force on the particle to be 0 at P. So
Force is 0.
Here's the particle, and the force is going to be down. Okay, and what we want, and it's a positive particle, right? It's a Q plus. I think it tells us it's positive, doesn't it?
Positive charge, yes.
Okay, it's positive. So we're going to put a parallel plate capacitor here. And what we want is this is the force of the magnetic field due to the magnetic field, and we need the force due to the electric field.
Okay.
All right, so what does it ask?
Electric field. Okay, with
What's the direction of the electric field at point P? It's got to be up.
Yep, that makes sense.
All right, and then determine the magnitude of the electric field in terms of the given quantities and fundamental constants.
It's gotta, wouldn't it just be equal but opposite?
The electric field is defined as the force on a test charge divided by the quantity of charge on the test charge.
Mm-hmm.
Therefore, the force is earthquake.
Mm-hmm. And then
So this, and they're asking for what the intensity of the electric
and this
field?
in that E is just gonna be this but negative, right?
No, this is magnetism.
Oh, but
This is electrostatics.
Oh, I thought.
So what we need is we've got a magnetic force that needs to be balanced by an electrical force. So this force
Oh, I see. Okay.
is equal to this.
Yeah, that's what I was trying to say.
Equals
Yeah.
Q.
Yeah. That's what I was saying. Yeah.
So now, see what we did here? Here's the magnetic force due to the magnetic field. Here's the electrostatic force due to the electric field. So you want to have positives down here and negatives up here. But they're not asking for, the characteristics of the capacitor. They just want to know what's the strength of the electric field.
Yeah.
So
Oh, cancel.
there it is.
Okay, cool. That makes sense. And then
Now, do you see how this is a sheet from goats? There's lots of stuff that a kid could do and get points for, but you got to be a stud. You got to know what the hell you're doing to get this and this.
wait, did we finish that last question?
Yeah, we did.
Determine the magnitude.
Of the electric field in terms of
Oh,
given
we did that.
quantity.
Okay, yeah. Okay, sweet.
That's an excellent question to ask. All right.
Sweet.
Okay, so
Is that everything?
page 661, 1 and 2. A charge of that many
Microcoulombs.
traveling at the speed of that much in a direction perpendicular to a magnetic field experiences a force. What's the magnitude of the field?
There we go.
Particle with a charge of that much and a speed of that fast
Charge, speed.
and uniform magnitude is that for the find the magnitude and direction of the magnitude of the force. That's going to be the same thing, except particle with a charge of that.
Charge, speed, and then B.
The direction of the magnetic force. All right, so they're not giving us a reference frame, are they?
No. Oh, but it says for each of the
oh.
cases in the drawing, find the magnitude and direction of the magnetic field on the particle.
Okay, so
Oh, we gotta do the sine theta.
yeah. So this is just going to be whatever the velocity is. That's just going to be Bqv, and then it's just going to be sine. Now here's the deal.
So yeah, we just do B times
This is
Q
30
times V
degrees,
sine
and
theta.
this is 150 degrees, 180 miles. So this is going to be 30 degrees as well.
Question: where do you? So from here, sorry, say that again. So 30 plus.
You know, let's see. It's sine. I'm going to do sine of 30. Sine of what is it? 150. also 0.5.
0.5. Oh, okay.
So,
okay.
but, and that's legit because the direction of the field is this, the direction of the velocity is that. So now,
Oh, I see.
so calculating that out is just going to be BQV sine theta.
Yeah.
Now, what about the direction of the force? Well, is it positive?
So it'll be the same answer, but.
Okay, so the field is to the right. The velocity is up. It's going to be into the page. The force is going to be into the page.
Wait, let me try that. So, wait, this.
Do for B.
Wait, which one? Oh, B is right. Oh, I didn't even see that one right there. I was just looking at that one. Okay, so you've got the velocity is this way, and then you've got the B field is that way. Okay, so yeah, the force is down.
And in each case, it's going to be down because there's a component of the velocity. There's two components to this velocity. One is parallel to the field, which is 0, and then perpendicular to the field. So it's the perpendicular to the field that counts.
Oh, I see.
And that, so in each case,
It's gonna be looking like that
That's
one.
what I'm saying.
That makes sense.
all right, so stop this.
But I